Hello, everybody. This is Professor Fineweaver, and today I'm going to talk to you a little bit about combustion analysis. So, combustion analysis is one of the harder topics in Chapter 3. It's kind of an old-fashioned way to figure out the subscripts in a hydrocarbon. So, here's the idea. Burn a hydrocarbon. Guess what two elements are in a hydrocarbon? Carbon and hydrogen. And hydrocarbon means it's just a general term for any X and Y, where X and Y are the subscripts on the hydrocarbon. So we're going to burn a hydrocarbon to find those subscripts, to find X and Y. So X and Y, of course, will give you the mole ratio of the carbon and the hydrogen in the compound. So how do we do this? We're going to measure the products, so the carbon dioxide and the water that are produced. So as it turns out, when you burn a hydrocarbon, you always get carbon dioxide and water. And the carbon in the carbon dioxide and the hydrogen in the water, those two things will give you enough information to find the moles of carbon and hydrogen in the original compound, and then that will give you the X to Y ratio. And of course, once we have that X to Y ratio, then that's exactly what we need for our empirical formula. So let's look at an example. Let's say we had an unknown hydrocarbon CXHY, and we're going to burn it. This is the fuel. To burn something, you always need fuel plus oxygen. And then with a hydrocarbon, CXHY is your fuel, you've got the oxygen, and then you'll get products, always CO2 and H2O. This is not a balanced equation. It's hard to balance because we don't know what X or Y are. I mean, we could balance it, but it would just have those variables that we don't know in there, so we'll just leave it unbalanced. Okay, so let's say that we're given a certain mass of fuel, so maybe we start with 0.373 grams of fuel, and then we add excess, so in other words, just plenty of oxygen, and then out the other side, we measure our mass here, and we get 1.13 grams, and we measure our mass here, 0.578 grams. And sometimes students will ask me, well, where did you get those numbers from? These are all given. You have to be given these, or you can't solve the problem. And these would be measured in the lab. Now, I said this was kind of an old-fashioned technique, but hydrocarbons are very important kinds of molecules. This is in all petroleum products, and this is a pretty easy technique to do. All right, so let's find the mole ratio. So we're given masses, we're not given moles. So we need to do our usual mass to moles for the carbon dioxide and for the water. And once we have the moles of carbon dioxide, we can get the moles of carbon. Once we have the moles of water, we can get the moles of hydrogen. And then we can get our X and Y. So 1.13 grams of carbon dioxide. Let's go to moles. We know there's a mole of carbon dioxide. We look up our periodic table. It's 12.01 for the carbon, 16 for the oxygen. Add them up and you get 44.01 grams of carbon dioxide for a mole of carbon dioxide. And we don't want moles of carbon dioxide, though. We want moles of carbon. So what's the conversion factor there? And this is often a confusing point for students, but it's easier than you might think. So how many carbon how many moles of carbon are in a mole of carbon dioxide, it's given by this subscript 1. There's 1 mole of carbon for 1 mole of carbon dioxide. So it's in the subscript. I know we don't write the 1, but the 1 is there. All right, so then if you punch this into your calculator, 1.13 divided by 44.01 equals, and you get 0.02567. So 0.250, I'll keep one extra digit for now, 68 moles of carbon. And I can do a similar thing for hydrogen. Sorry, for water. So a mole of water, again, I get out my periodic table, 2 times hydrogen, 1 times oxygen, I get 18.016 grams of water. But now it's 2 moles of hydrogen for each mole of water. So this step is important because if you didn't do it, you'd be off by a factor of 2 here. And that gives me my moles of hydrogen, and 0.578 divided by 18.016 times 2 equals 0.06417. I've only got 3 sig figs. All right, so, oops, I had a mistake here. This was supposed to have a 0 in there too. If I go back and look at the number, that's got a 0 in there too. All right, so now I'll divide both by the smallest number. And the smallest number is with the carbon, so divide by 0.02568, just like we would do with an empirical formula, and that gives us 1.00 moles of carbon. Divide this by 0.02568, and that gives us 2.50 moles of hydrogen. So it's CH2.5, but I need to express that in whole numbers. So it's C2H5. So that's my empirical formula using combustion analysis. All right, so that's my example for you. Then I would say you guys should do a sample problem, and this is going to be on Moodle. But just to give it to you now, given you have a hydrocarbon that's burned, so CXHY, you need to find the X and the Y. Products in this case are 185 grams of carbon dioxide and 63.1 grams of water. Notice I'm only giving you the mass of the 2 products. That should be all you need. We never used the mass of the fuel going in, so we didn't need that. There are sometimes problems where if this isn't just a hydrocarbon, but if it's a carbohydrate, so if there's oxygen here, then you need to know the mass of the initial fuel, and you can figure out the mass of the oxygen present by subtraction. But for now, see if you can find X and Y given this information, where these are the mass of the products. All right, that's it.